Welcome back to ECE 320A. Hopefully you had a productive 3-day weekend. Now you're ready to begin your long semester push for ECE 320A at least. A few announcements. Homework number 1, please watch the website, but hopefully I'll have that available by Thursday, and it will be due Thursday night. No, hopefully you have a little bit more time to work it than that. You should be or have already read Chapter 10. That's what we're going to be covering now in the first part of the class. I unfortunately have another meeting scheduled for the morning of Thursday, this coming Thursday. You may not have that many office hour requests anyway, is what I'm hoping. But normal office hours are 9 to 11 on Thursday. And that will kick in next week officially. It officially starts now, but I have another meeting. So if you need to see me, send me an email or see me after class, and we'll try to make the connection that's necessary. You should have submitted your passport. If not, don't do it right now. You can do it after class. It's not due until 11:59 this evening, your passport. What I want to do for goals today is someone reminded me that if you're on track, you have 351A this semester along with 320A, and because of that you have a class from 1 to 2 on Wednesday. So the first part of business today is to vote on office hours. That's going to be part of your in-class participation, and I did grade your previous in-class participation. It would help me in terms of grading for you to simply write down what you can get when I say stop. Don't go ahead and take notes and follow along if you can. Just put that paper aside and turn that in. That gives me a better indication of where we are as a class, what you know, what you don't know, or what you didn't know up until that point in this presentation of the material. It's not really held against you, although I did grade this out of 10 points. I didn't yet enter those in. Hopefully I'll be able to put those in so that I get an average as far as the class is concerned relative to that particular problem. And it was more for me to assess where are we as a class, not so much for your particular point total. It's more your participation that you're getting credit for. Okay, so don't get too hung up if you received a 0 or a 2, or if you got a 10, don't necessarily think that you've got the class by the tail, so to speak. So we'll vote first on office hours, and then we'll get into Chapter 10 material, which is sinusoidal steady-state power, single phase, which I may just write as 1-phi. So that's single phase power. We'll move on in Chapter 11 to 3-phase, so you'll see that as 3-phi. But we'll start with a generic element, look at the instantaneous power and the average power of that generic element. Then we'll look at each of the 3 generic passive elements, resistors, inductors, and capacitors, try to understand the power associated with those, not only the instantaneous power, but other kinds of power so that we can keep track of these power concepts. And true to form, we'll have another quiz. And that you can put on the bottom of this first in-class participation. This now, take out a blank piece of paper, put your name in the upper right-hand corner. Make sure it's written fairly cleanly so that I can read it and not spend too much time trying to decipher whose paper this belongs to. We're in the political process, so I decided we would have a write-in candidate, meaning if you don't like A, B, or C, or if A, B, or C do not work for you, you can vote for D, which is a write-in time, and I'll try to see how this works with my schedule. The first A vote, so you could just say office hours A, office hours B, office hours C. I guess you could put all 3 if they all 3 work for your schedule. But If they don't, vote for those that you think work best for your schedule. Meaning, we're going to keep the Thursday, 9 to 11. I think that worked. Is that true? Does that work for most people? So here's your second set of 2 hours that you're voting on, if that makes any sense. Vote for A, B, C, or all of the above. If none of those work, give me a write-in, and I'll go back and try to figure out a better time. Is that making sense? That's part of your in-class participation, or maybe one of your in-class participation. Maybe we'll have 2 of those today with the quiz counting as your second in-class participation. Let's then move on from that. That shouldn't take you 10 minutes to do, hopefully. And now let's talk about power, which is the single-phase variety discussed in Chapter 10. To get us started, let's just look at a generic device, and we'll label that as the positive terminal and the lower one the negative terminal, and we have a current then going into the positive terminal. Going into the positive means it goes to that terminal before it physically might go to the element. That particular terminal is labeled positive, and this is then the passive sign convention, meaning we are going to assume that when we have this I current going into a positive terminal as drawn, we will assign that a positively absorbed power. That will be absorbed power. So V times I, this is now positive VI, is absorbed. If it turns out that you do the calculations and I ends up being negative, you put that negative in there, that algebraic negative in for the I, and you would end up with a negative power absorbed, or actually a supplied power. Is that making sense? That's what we're meaning by the passive sign convention. Let's now, typically we might say, well, we have a voltage, V of t, that has a maximum amplitude, V sub m. We'll stick with the cosine in terms of the sinusoidal components, omega t plus theta sub v. And the current could be similarly defined also in terms of the cosine. And generically, it has its phase angle, theta sub I. Now, it gets a little confusing. Well, it makes it cleaner if we actually do something a little different. All we are really worried about is this difference between the voltage phase and the currents phase. And because we're really only interested in that difference, these have been going sinusoidally for all time, we're going to say. Now they are aligned in some pattern based on the phase of the voltage and the phase of the current. And we're really only interested in the difference between those. So let's define our t equals 0 location where the current reaches its maximum. Meaning we now have determined that we really only want I of t to be written as I sub m cosine omega t. And we'll explicitly denote that there could be an angle associated with the voltage and an angle associated with the current by keeping track of that as theta sub v minus theta sub I in the argument of our voltage waveform. How would I write these? So maybe going a little bit backwards, how would I write this in terms of RMS quantities? So you might see me doing it this way. And for power reasons, sometimes it's more convenient to write these magnitudes as RMS units. Okay? So those are two ways of expressing the voltage and current But what I had just said relative to our time reference, what we actually want to do is select this t equals 0, or select our time t equals 0. We can sort of slide our time axis around and just pin it down where we want it. Let's pin that so that our current is hitting its max at that particular point in time t equals 0. Select t equals 0 to be hits its maximum or peaks. And if that's the case, now we will write v of t as v sub m cosine omega t plus theta sub v minus theta sub I, and I of t is equal to I sub m cosine omega t. So that's sort of the same way of writing the information that we'd previously written down. This is now how we will refer to the voltage and the current. Now that we have that structure, let's now look at the instantaneous power. That should be clear that it's simply the product of voltage and current. That's the instantaneous power. And I can now multiply those two expressions for voltage and current, and I now have v sub m I sub m cosine omega t plus theta sub v. I'm going to hit a carriage return, but you have probably a wider piece of paper. I could keep going, but that might frustrate you. So, well, maybe I will do that. Let's see how wide I can go. Minus theta sub I, and then I'm going to multiply that times cosine of omega t. So that goes up there. Is that acceptable to do it that way? That's the product of voltage and current. And this is getting a little bit messy, but we'll follow through with the mess. That's why we go into phasor notation. Oh, and in the grading of this problem that you worked on Thursday, I noticed some confusion, well, some things that I would like for you to not do in the future, and that's to mix time domain and frequency domain, or time domain and phasor. If you have cosine omega t, don't be multiplying it by a complex number or a phasor. Realize that, oh, I now want to have that sinusoid as a phasor, then I can multiply that by a complex number, and then I will get a complex number, and I can represent that or write that as a phasor. So don't be writing cosine times a complex number equals some other cosine. Hopefully that will start to make sense. So if you're playing, we like to play in both areas, time domain and frequency domain. And you want to be comfortable playing in both of those domains, but don't mix them up. If you jump over into the frequency domain, play in that domain and then come back when you need to. But don't be mixing the two domains. That was sort of an aside. That was our commercial, I guess. But did that make sense? This is what well, we'll move on. This is now a product of cosines. What I want to do is rewrite that a little bit more cleanly. And now I need to remember my trig identities. Cosine alpha times cosine beta. Does everybody have those memorized? Those are implanted in your noggin somewhere or your noodle. Well, if it's not, how could you derive that? Now you're going off into some trip and you forgot your trig tables and you go, oh, well, I can derive that. Well, yes, you can. Because what do you remember the cosine of x is? In terms of complex numbers, that's e to the jx plus e to the minus jx over 2. And now you can just do some algebra and derive this particular relationship. I'll let you do that on your own. but you should be able to now have cosine alpha as a combination of complex numbers, multiply that by cosine beta, and now you just have to combine your product of e to the jx, or e to the j alpha plus e to the minus j alpha times e to the j beta plus e to the minus j beta, and group those to where you actually end up with 1/2 cosine alpha minus beta plus 1/2 cosine alpha plus beta. That's the trig identity that I need to help me simplify this expression, where alpha is omega t plus theta sub v minus theta sub I, and beta is omega t. If I take the difference of those, I lose the omega t. I lose the time argument inside the cosine expression, and that now becomes independent of time. And I have cosine of theta sub v minus theta sub I. Is that clear? And if I add them, I end up with twice the frequency, 2 omega t's. Using that now, I have this instantaneous power is now v sub m I sub m, and I can't forget that 2, 1/2. And then I have cosine of the difference of those arguments, and the difference just leaves us with that. There's no time variable inside the argument of that cosine. And then I also have Vm Im over 2 cosine of 2 omega t plus theta sub v minus theta sub I. That's our instantaneous power. Questions on that? And now maybe it's kind of ugly to think about cosine 2 omega t plus a shift, so let me get rid of that. Let me just rewrite this piece by using another identity of the sum of two angles, cosine of alpha plus beta. And that will now allow me to isolate my cosine and sine of 2 omega t. Meaning now I want to use another trig identity for this piece. And what I want to do in that piece is say, oh, cosine, maybe I should make these different since they're not necessarily the same in this particular discussion. I now have cosine alpha 1 cosine beta 1 minus sine alpha 1 sine beta 1, where I now want this piece to be alpha 1 and this piece to be beta 1. If that's the case, I can now rewrite my instantaneous power as P of t is 3 terms. I can't forget this piece. That piece is still there, and now I've just split the second piece into 2 parts. And I now have this 1/2 Vm Im cosine theta sub v minus theta sub I plus a couple more pieces. 1/2 Vm Im cosine of theta sub v minus theta sub I. That's actually my cosine of beta 1 times cosine of 2 omega t. And I have the sine piece minus 1/2 Vm Im sine theta sub v minus theta sub I sine of 2 omega t. That's now an expression for the instantaneous power. What's that going to look like? Well, if you had voltage and current in the structure that we started with, what was their frequency? It was the same, wasn't it? The voltage and current were both oscillating at the same frequency, and what was that frequency? Okay, in terms of radians per second, what was the frequency? Make it easier. I wasn't meaning to have it in hertz, but we started back here, didn't we? That was our expression for voltage and current. What was the frequency? Omega. What's the frequency of the power? Instantaneous power. It's 2 omega. The power is now oscillating at twice the frequency of our voltage and current. That's something to keep in mind. Okay? Your power is now oscillating twice as fast as your voltage and current waveforms were oscillating. That's what we've learned by just looking at this instantaneous power. What if I now say, you know what, I don't care how hard that's bouncing back and forth necessarily. I just want to know what's the average power absorbed by the load. If I now average this instantaneous power over one period, and now I could say the period corresponds to the voltage or current period, it would be associated with the omega. Omega is 2 pi f. That's what you are supposed to memorize, right? And f is 1 over the period. So omega is 2 pi over cap t, where t is your period. If we integrate this instantaneous power over one period, what's going to happen when we have a cosine and a sine of 2 periods? 0. Those last two terms are going to go away when we average this instantaneous power over one period. So if we now look at the average power of this generic element, this was just a generic element that had a voltage waveform and a current waveform that we had arbitrarily established at a frequency of omega. We say, what's the average? Well, that's simply 1 over t, the integral, p of t dt, and isn't it nice to know that you're actually using your calculus? Your second semester calculus, now you have an integral. Now you're using that stuff. Well, you're actually using it all the time in this class, or we will be. So there's your average power, and as we just discussed, if we have 2 cycles in that interval, those are going to integrate to 0. We're going to have exactly the same amount of positive area as negative area. So those last 2 terms in that 3-term expression for our instantaneous power, those last 2 terms are going to go away when we concern ourselves with the average power. Instantaneously, that power is moving up and down at twice the frequency. But if we just want to know the average, what is our average power then? What happens if we integrate this p of t? We've concluded that these two go away, so let's minimize our effort. Let's just know that and write that down. What happens when we integrate this? Cosine theta sub v minus theta sub I. The key to realize, as is just being pointed out, is that that argument does not contain the variable t, does it? So that cosine of theta sub v minus theta sub I is just a number. That's a constant. Now we integrate a constant. That's about as easy as you can get. We integrate a constant for a length of time capital T, and we're dividing by that capital T to get the average. What are we left with? Just that very first piece, that first term. That's our average power. And this actually may, in parentheses, they may call this the average power, they may call it the real power. We'll be interchanging those 2 labels for this power term. This now, because the cosine 2 omega t and sine of 2 omega t terms whoops, integrate to 0, we have our P average is just 1/2 V sub m I sub m cosine of theta sub v minus theta sub I. Or, what if I wrote that in terms of RMS values of V and I? I could factor that 2 as a square root of 2 times the square root of 2, and now I have Vm over the square root of 2 times Im over the square root of 2, and what are those two pieces? Those are just my RMS values for V and I. Is that making sense? I now have factored that 1/2 into 2, and I could write this as V RMS I RMS cosine theta sub v minus theta sub I. And this real power, or this average power, is actually the power transformed from electrical to some other form. Maybe I should say, whoops, the real power is a measure of the energy transformed from electrical to non-electrical energy. Meaning now maybe we've converted this electrical into heat, or maybe we've converted it into mechanical. We're now driving this machine, this motor. It's driven by voltage and current, and it's now moving some shaft, or it's moving something. And that's then the average power tells us how much we're converting back and forth, well, from the electrical domain into some other non-electrical domain. That's the real average power. Questions on that? That's this guy. It's important to the power company. They have to actually deliver this voltage value and this current value. They need to supply that. What we actually get is this P average, which is some fraction of the V and the I. The power company, what you could sort of say is they see this as the apparent power. Here's the apparent power. Apparently, you're needing this V and this I. And as it goes through the system, because of these losses or these reactive, maybe I shouldn't say losses other than in the transmission lines, but the reactive elements introduce these phase shifts. And that cosine of the difference between the phases gives us the fraction of the apparent power that we actually see. And one way that we denote that or label that is by a term. This is a new term, and that's the power factor. That might be a capital PF, it might be a lowercase pf, but that's actually just taking the average power and dividing by this apparent power, and what happens when I divide P average by VRMS IRMS? I just get that cosine piece. So the cosine of theta sub V minus theta sub I is the power factor. And that might be 0.8. It might be 0.9. It might be 0.95. We actually want that to be as close to 1 as possible, to be as efficient as possible. We want the power factor to be close to 1. If you're an industrial plant or facility and you have a power factor of 0.6, the power company is probably going to surcharge you for that low power factor. And we'll look at how we can move that power factor closer to 1 by adding reactive elements. That's where we're headed. But we need to keep track of that because that's important. In order to get there, to understand that better, let's look at the individual pieces. And by the individual pieces, I'm meaning these standard pieces that you now should be getting very comfortable with, R, L, and C. Let's look at what each of those pieces do when we observe their power. So let's look at these different impedance values. And let's start with the easy one, where our impedance is R, a pure resistor. What do we know about the relationship between current and voltage of a resistor? How are they aligned? If I said sketch the voltage, or maybe I sketch the voltage waveform and I now say sketch the current waveform for a resistor on top of that voltage waveform, how would you sketch it? The peaks would all be aligned, the nodes would all be aligned, they would be in phase, wouldn't they? They're oscillating exactly together. The current and voltage are in phase. Or in our terminology, our voltage phase is equal to the current phase. So the power factor on this pure resistor is what? We plug this information into cosine, theta sub v minus theta sub I. You pick which one you want to replace. Theta sub v is theta sub I. Now I have 0 for my argument on the cosine. Cosine of 0, 1. So what you really like is if you are this industrial plant, you look like a pure resistor. That's the most efficient use of energy. Now, what is then, if you've already answered this question because of your insight into what we had just talked about, what's the expression for P average? And those are numbers. Those are not phasors. V sub RMS is just a number. I sub RMS is just a number. I didn't bar those, so be careful. Sometimes I forget to bar things when they are phasors. These are not phasors. These are numbers. If you know the RMS voltage and the RMS current magnitudes of a resistor, you know the average power absorbed by that resistor. That's all there is to it, and that's why I said that's the easy one. Now, to learn more about the others, have you heard that expression? ELI the ICE Man. Maybe that is associated with when you took ECE 220. Or who instructed you in ECE 220. ELI and ICE. Well, this is something else you want to know until you retire. It gives you an easy way to remember relationships, current and voltage of an inductor and a capacitor. ELI has an L in it, so that must be the inductor equation. And ICE has a C in it. And E is voltage, it's electromotive force. So E is the electromotive force. That's where the E comes from, but that's really our V. All right, now how do we use ELI and ICE if we haven't seen it before? Well, ELI is the voltage-current relationship of a inductor. And this just says V of t, which is of the inductor, is L the I sub L of t dt. And you use that relationship to actually find the impedance of your inductor. You look at them in the time domain, you take the derivative of your time domain current, and you'll find what's left over, and you see, oh, j omega L is the impedance of my inductor. Similarly for the capacitor. This is now I, and that's sub C of t, is equal to C dV sub C dt. And those you need to commit to memory. But if you just remember Eli the ICE Man, you've got it. And what's the other thing that will be important for us now that we're talking about power? We'll be reading English-wise from left to right. In terms of voltage and current, voltage is coming before, or the current is lagging the voltage in an inductor. It's coming later. So this is another way to remember, oh, I can't remember leading or lagging. What is it? Well, if you remember Eli the ICE Man, you have it. You just look at this and you say, okay, this is the inductor equation. I know that the I is lagging the voltage in an inductor. That's one way of remembering those distinctions. Similarly with your capacitor. With the capacitor, the current is coming before the voltage, or it's leading the voltage. And this will make more sense when we start talking about power. We'll have a power factor, and somebody's going to say, is that a leading power factor or a lagging power factor? You need to know. You need to know more than just the number if you want to go a little bit more in depth as far as how you want to correct for that power factor. What I'm wanting to say here, and we'll get more into this, is current lags voltage in an inductor. And here we can say that current leads voltage in a capacitor. Now that we have that insight or intuition simply from Eli the ICE Man, let's now look at the second element, which is an inductor. With an inductor, what's its impedance? That's J omega L. But sometimes it's easier to just say, well, that's J times some X sub L, where omega L is buried inside X sub L, and this is our inductor relationship. And what's the sign of that, or what's the polarity of that impedance? The argument, the sign in front of J, it's hidden. It's not explicitly there, but it's a positive, isn't it? So that's a positive sign on the inductor. Now, what do we want to do here? So this, now we know that the current lags the voltage, and what's our average power? Or, well, maybe we need to look at this a little bit more carefully. We know that the current lags the voltage, but we also know something. If this is a pure inductor, what do we know about how much it lags? By 90 degrees, doesn't it? Because of that J. Meaning if we had our V phasor, which is Z times the I phasor, we know that that's Ohm's law generalized to an impedance. V is equal to Ri. Now it's V is equal to Zi, where V is a phasor and I is a phasor. Let's now replace what we know to be true in this relationship to see that that 90 degrees, if you don't see it just yet, where that's coming from. In general, the V is some V RMS at some angle theta sub V. And that's equal to, and what's the impedance Z of an inductor? You said that's J omega L, right? And the current, we just know that that's I RMS at some theta sub I. What else what do we also know about J? If you had to sketch J, if you now looked at J in a two-dimensional plane of real being in the horizontal and the imaginary in the vertical, where is J? That's right up there. That's that 90 degrees. That's on the y-axis in our two-dimensional complex plane. J corresponds to an angle of 90 degrees. If I now write J omega L in a phasor way, I can now write this as J, whoops, it's not what I wanted to do. I wanted to write that as omega L at 90 degrees. And the positive sign says we're going up. We're going in the vertical up direction. Now I have omega L at 90 degrees. And what do I know about these relationships? My angles have to be the same and my magnitudes have to be the same. So if I equate my angles, this expression has now convinced me, I hope, that the angles differ by 90 degrees. From this expression, I see that theta sub V is 90 degrees plus theta sub I. Or theta sub I is equal to theta sub V minus 90 degrees. So the current lags the voltage by 90 degrees. It's minus 90. And if I looked at theta sub V minus theta sub I, that's 90 degrees. Now we can go back and look at this average power. What was that expression? That was our expression, wasn't it? And now we know what theta sub V minus theta sub I is. That's this guy. And it's a good thing we learned our trig, at least some of it. Cosine of 90 degrees, hopefully you remember that that's 0. So the average power, the real power of an inductor is 0. What in the world is going on? Let's look at our, so this says no real or average power of an inductor. All right, so now we're scratching our head, and the question you might be asking is, where does this go? Or let's just look at one. Let's say, where does the current go? What's our instantaneous power? We derived that for a generic element, didn't we? P of t. We didn't have a subscript on it, so we have exactly the same structure for P of t. Let's just subscript it with an L, and occasionally we'll put in what theta sub V minus theta sub I is. It's 90 degrees. But before we do that, let's just follow it along. This is now 1/2 Vm cosine of theta sub V minus theta sub I. That shouldn't surprise you. That was our real power piece, and that's going to vanish. Then we had our second piece, I'm making sure you're awake. That's a 2 squeezed in there. That was twice the frequency, wasn't it? Our power. But what happens to that piece? It also goes away because of that cosine. And what was our last piece? So what's our instantaneous power look like? It's just that last piece, isn't it? What's sine of 90? That's 1. So now we can just absorb that. And we now know this is our instantaneous power on the inductor. What's that saying? Well, instantaneously, how quickly is it oscillating? Twice the voltage and current speed or frequency. What's going on? We have no real power, and something's going because of that inductor. We just have an inductor, and it's doing what? Well, its power is oscillating at twice the frequency of the voltage and the current, and the power company wants to know that. You can't just hide because you're going instantaneously. Just because you have 0 real power doesn't mean something's not happening. What's happening? Well, this is going positive and negative, isn't it? It's a sine wave. See? It's going in all sorts of frequencies. No, it's just 2 omega t. But this is now going like this. What's its nominal level? Centered around 0, isn't it? So it's going up and positive as much as it's going negative. Well, what's that doing? Well, what's an inductor? It has a magnetic field, doesn't it? So now you're energizing that magnetic field when it's positive, and then you're de-energizing it or sending it back to the source. So you're just playing catch with the source. Here, I'll take it. No, I'll give it back. No, you have it back. No. So you're just going back and forth with this current and voltage, this power. You're trading it back and forth with the power company. They have to create that in order to keep that happening. So this instantaneous power, let's just write some information down that we've now learned. The instantaneous power is twice the frequency of the current and voltage. And this piece of L of t oscillates. And when it's positive, when p sub L of t is positive, then we are actually storing energy in the magnetic field. When it's negative, because this is sort of that passive sign convention, when it's positive, the load is taking something, and when it's negative, it's giving it back, it's supplying it. So when it's negative, we're saying that the energy is delivered back to the source by means of that magnetic field collapsing. It collapses and gives it back. Then it comes back. So it's like an oscillator. And we need to keep track of that. Because what's happening? Well, there's probably some resistance on the transmission lines as you're going from source to load. And what happens to all of that voltage when you have voltage or current going, let's say current going through a resistor? what happens? Heats up. We have some I squared R losses. So if we're throwing current back and forth, we're actually losing some power in the process. So we're concerned about that. The power company has to give us a lot more voltage in order to meet the voltage demand at the load. Okay, so we would like to keep track of that. Well, we might not, but the power company does. So, and if you're working for the power company, obviously you want to keep track of it, right? So you want to pay the bills or collect the bills that are accruing. We would like to keep track of this energy since the current is actually flowing on the lines between the source and the load. And the way that we keep track of that is we define a new term. Our real power was labeled with a what variable? Capital P. Now we're going to watch our P's and Q's in this chapter. So reactive power is a Q. We're going to label reactive power with a Q, and we're going to call that then this VRMS, IRMS, or the 1/2 Vmax Imax sine of theta sub V minus theta sub I. And a lot of times, actually, we may get tired of writing that theta sub V minus theta sub I, and we may just call that the generic theta. Theta is the difference between the voltage phasor and the current phasor. We may just subscript it, or I'm sorry, label it as theta. We also want to keep track of these P's and Q's. P's had units of, we didn't do it, did we? Watts. We didn't say it today, but it is units of watts. That's our hairdryer, which none of you use anymore, right? But maybe you have some lighting in your home and it has so many watts or uses so much, or maybe you have a microwave, that's in watts. This one we are going to label as volt amperes reactive. That's the unit of Q. And I don't know that we'll use it that much, but there is analogous to the power factor, we also have the reactive factor, which is the sine of theta sub V minus theta sub I, which we might denote as RF. And the other thing that we want to learn from this maybe we do not have a purely inductive load, but maybe it looks more inductive. What do we know about the current and voltage in an inductor? ELI, right? ELI. Where's I? Well, it's lagging the V. So in an inductive circuit, we know that the current lags the voltage. And because of that, if we looked at this difference and we called that theta, what do we know about the sine of theta? If, let's say theta sub I is behind theta sub V, current lags voltage, just put some numbers in here. Let's say this is 10 and this is 40. What's this? 40 minus 10 or 30, that's a positive number. So theta is positive. Theta is bigger than 0, and we call that, and so if this is true, if we go back up here to how we defined Q, Q is VI sine of a positive angle. What's the sign of Q? Positive. If we have theta positive, Q is positive, and we refer to this as a lagging power factor. All of that was for an inductor, right? Or an inductive load. If our system, if our load looks more inductive than capacitive, we're going to get a positive Q. And we'll call that a lagging power factor. Question? So what we want, the question was, we want to, well, yes, the question was, ideally we want to drive our power factor to 1. We want to drive the angle theta to 0. We would like to align the current and the voltage. That's the ideal. Sometimes we can't do that. We just have so many machines in our plant that it's going to look inductive. What we try to do, though, is get that power factor closer to 1 if we can't get it all the way to 1. So our goal is to try to make that power factor 1. We may not be able to. And in this class, I may just be asking you, what's the power factor? And you'll just have to compute it. And maybe it will be 0.7. Maybe it'll be 0.5. But you'll know something about your system when you compute that number. Does that answer your question? Let's now move to the next circuit element, which was a capacitor. And what does its impedance look like? If I said, what's the impedance of a capacitor? You can say it all sorts of different ways, can't you? I remember it as 1 over j omega c. But maybe that's not the way I want to write it here. Maybe I want to write it in terms of j. Well, if I can multiply that by 1, j over j, and j squared is minus 1. So now I have a minus j 1 over omega c, or that's minus j, let's say x sub c. And this is for a pure capacitor. What have we said today about the current and the voltage? If you forget, just remember ice. We're in the desert. You like ice. Yes? So ice tells you the relationship between current and voltage. Now we know that the current leads the voltage. And if we did all of our angles and our relationships, we would find that theta sub I is equal to now theta sub v plus 90 degrees. So this now says that if I looked at theta sub v minus theta sub I, I'm now minus 90 degrees. Or if I looked at the angle of minus j, now I have j, oh, that's going up, but the minus sign moves me 180 degrees, so I'm actually minus 90 for an angle. Many different ways of thinking about that. But what's your average power of a capacitor? And that shouldn't surprise you based on what we've learned with the pure inductor. So this is looking similar to the inductor, except this one is just the opposite in terms of sign, so to speak. But now we have, if we went through, we would find that our instantaneous power on the capacitor also oscillates. In this case, when P sub C of t is positive, we now have energy stored in an electric field. And when that P sub C of t, it's flopping around at twice the frequency of voltage and current. When it goes negative, now we have this electric field collapsing and giving back the energy to our source. So our energy, whoops, what did I, you guys are supposed to wake me up. The energy is stored in the electric field, not energy in electric field. The energy is stored in the electric field, and here with a negative, the energy is delivered back to the source. It behaves 180 degrees differently than an inductor. The question was, it behaves like an inductor. Yes, it does behave like an inductor, but they have complementary behavior, meaning I can effectively, with an inductor, which way is our Q? Up here. With a capacitor, which way is our Q? Down here. I can use those to cancel each other out or to help offset each other. So the inductor goes up, the capacitor goes down in our complex plane depiction of the component of our inductor and the component of our capacitor. So those two are going to play against each other in the way that they oscillate. Question? I'm sorry, did that answer your question? Oh, no, what I'm saying here, so the question was, should it be just the opposite in behavior? Here I'm saying P sub C of t, that's my capacitor power. When it's positive, this energy is stored in the electric field. That's how I'm defining the power, the instantaneous power. It's now building up the electric field in that capacitor. Then it's going to give it back. Well, what's going to happen is when the inductor gives back its power, the capacitor is going to charge, and they're just going to sort of throw these back and forth more locally than all the way between source and load. So I really didn't put these in time with each other when I'm saying P sub C and P sub L. I'm just saying P sub C, if it's positive, it's going to charge the electric field or store the energy in the electric field. Yes, so they're going to, one's going to be storing and the other's releasing, and they're going to be doing that in a complementary fashion. That making sense? There was another question, but did that answer? Okay. Now, what we can say then is if we have a capacitive circuit, it wouldn't necessarily be purely capacitive, but just more capacitive than inductive. We now know that the current leads the voltage, and we know this relationship between V and I. What do we know about theta now? It's negative because I is bigger than V in magnitude. Theta sub V is bigger than theta sub I in magnitude. That's going to be negative. If we go back to the expression for Q, Q was VRMS IRMS sine of theta sub V minus theta sub I. That's now a negative argument. What's the sign of a negative angle? Negative. So our Q is negative in a capacitive circuit. This says then that Q is less than 0, or we have a leading power factor. Those are our three pieces, R, L, and C, and typically we're going to have them combined in some complicated way. We're not just going to have an R, we're not just going to have an L, and we're not just going to have a C. We're going to have a mix of those. And if we have a mix of those, what's our impedance going to be? If I had a load and it had some resistance, it had some inductance, and it had some capacitance, how could you, in one adjective, help describe that impedance? You would say it's complex. You have a complex impedance. Not that it's complicated, but because it's a complex number type. Is that making sense? It might be complicated, but we're just going to refer to that as complex impedance. Well, if we have complex impedance, why don't we just talk about complex power? So far, P and Q have just been numbers, haven't they? But let's now add those up vectorially. And how will we do that? Well, we'll introduce a vertical direction with the J. So now what we want to do is we want to create something that maybe you haven't seen before. Now we're going to call it an S. That's our complex power. That's going to be made up of these two pieces, our real power or our average power and our reactive power. And we're going to combine those vectorially in the complex plane. So we're going to call our complex power P plus JQ. Now let's put in what we know those to be. We have VRMS, IRMS, cosine theta sub V minus theta sub I. That's P. What's Q? Remember how we define Q? We're going to scale that with J, or add that in with J. That was VRMS, IRMS, sine theta sub V minus theta sub I. And now this is one of the reasons why you probably gravitated to engineering, is you like to mess with algebra. You like to play with algebra. And now this might be screaming at you. Maybe not. But maybe you see something buried there. A different way of expressing that. Think Euler. What's cosine x plus j sine x? E to the jx. It's right there. Meaning, factor out the v and the I. And I have e to the j theta sub v minus theta sub I, right? Because e to the jx is cosine x plus j sine x. This is now just a quicker way maybe to write that earlier expression. Now that I have this, let me play with it some more. This is now, well, my voltage is a phasor. It has a magnitude, V, RMS, and an angle, theta sub V. Okay, that's my voltage phasor. What's my current phasor? Well, it has a magnitude. What's this? I can't drop that sign. But I now have a minus angle. That's not too bad, because we know how to negate an angle in a complex number. What do? We conjugate it, don't we? So if we conjugated the current phasor, we would get this. This is just the conjugate of the current phasor. I've just derived another formula for complex power. It's the voltage phasor times the current phasor conjugated. So if you know the voltage phasor, and you know the current phasor, you've got the complex power, which tells you what? It tells you more than just the average power, it tells you the reactive power. And you can say whether it's inductive, capacitive, etc. What I'm trying to tell you is that we now have this expression for VRMS phasor, IRMS phasor conjugate. And the units that we will give this volt amperes. That's S, where S is actually a complex number. So I could maybe put a bar over it. That's a complex number. That's our S. That's the complex power. So if you have a load and you know that load's voltage in phasor form, and you know that load's current in phasor form, you can get the complex power of that load, which consists of real and reactive power. We have the watts, we have the volt amperes, that's the complex power. We have the bars, volt ampere reactive, which is the reactive power. And if you wanted a different way of thinking of this, one way to think of that is through a triangle. We have P, we have Q, and we have S. And what's this angle? Now you could give me the real power, you could give me the reactive power, and which way you go with the reactive power, up or down, depends on whether you have an inductive or a capacitive load. We have to make sure we're treating things vectorially. And you could also, now with this power triangle, complex power, you know that you could take the magnitude of the, and what's the magnitude? Well, this is now magnitude of S cosine theta. That's our real power. So we could get it many different ways, and Q now, in the vast amount of time left, I want to give you a quiz. Oh. So here's the quiz. If we have that circuit from Thursday, what's the complex power supplied by the source? This is 2, this was J1, this was 78, and this was J59. This was V sub L, which I'm mixing time and frequency, and I told you not to do. And you can add this on to the bottom of your vote for the time, office hour time if you want. But this was there, and what was this as a phasor? We could say in RMS it was this. So what was I asking for? I was asking for, let's see if I can even express it. Find complex power supplied by the source. So first off, you need to know, does that even make sense? And in the minute you have remaining, just outline how you would solve that problem, if you have an idea. How would you solve that problem? What would you need to find? How would you approach that problem? Based on what we've tried to explain today. You have the tools, if today's lecture made sense. And that's what I want you to think about when you're reading chapter 10 and when you go home tonight and before Thursday. I want you to have a good idea of how you would find this complex power. You may not know it now. Write down what you think you know now. Turn that in as you leave, and I'll see you Thursday. Just in an outline, you could try to explain. So if you were telling somebody, this is how I'm going to solve the problem, this is how I would do it, maybe in 3 steps. Just write down an outline form of how you would solve that problem. Does that make sense? You don't need to put numbers in because I know we're short of time. We're actually out of time. Thank you for being patient and tolerant of me running over time. I will see you on Thursday. Remember, no office hours on Thursday. If you need to see me, send me an email or we can talk that way. Leave your 2 in-class participation points here on the table, and hopefully you found your returned in-class participation from last time. I'll see you on Thursday. Have a good remainder of Tuesday.